So I'm going to discuss some topics related to dynamics and equations. First, complex curves or hyperbolic surfaces. And then again, talk about some results that I've done going to our question. But I'm not going to step over all of that. So it will be long before I even do the theorem or state the theorem. So maybe I'll start from, okay, so the discussion is about, so the certain natural flows that I want to motivate defining the flows, define over some bundle. So I don't use this over mg, which is the moduli space of space. Hyperbolic surfaces, or if you prefer, complex curves of genus over different structures on the surface. Maybe it's a hyperbolic structure, complete hyperbolic structure on this compact surface of a finite volume, or it's compact and finite, or you have a complex structure and you have the moduli space of all possible complex structures that you can put on a surface of genus G, and then we want to find, we will see how basically deforming the complex structure, or actually the bundle here is essential. Changing the structure and seeing what happens to the structure can help you get results about properties of a given hyperbolic surface, or in this case, what will be a complex curve plus some additional structure. Before I define anything or say what I mean, what the flow is, how we define it, what I mean by dynamics over this, maybe I want to discuss a few problems, a few questions, just to motivate the work that I'll be discussing. And so, if you have heard any talk about anything related to these topics, the first example is usually billiards and this trajectory of a ball in the billiard table, but I don't want to start from billiards, so I'll keep the billiards for the last example, but we'll get there. So I'll start from a purely combinatorial question. Which, I mean, even though it's a combinatorial question, it's certainly related to surfaces, that's why I'm mentioning it. Topology of surfaces, which starts from basically, you start with an interval and you divide it into n pieces. Here I'm dividing into 4 pieces. And one side of the interval you put, I mean, there are different versions of this. You put, so this small n is fixed, but you put capital N semicircles with all the same centers, for example. This doesn't have any respect for this. There's nothing about this interval. And the other side, on each, so if I did it, well, I mean, on each interval, I'll have an even number of, so then I will have A1, A2, A3 to AN, and I just put, so somehow n capital N is fixed, and A1, you can imagine A1 to AN are somehow random integer points with sum is equal to n. And one side of this interval I'm putting for AI, I put A1, I put A1 semicircles. For A2, I put A2 semicircles with the all centered at the center of the interval, and A2 and AN. So this way, given A1 to AN, with sum is equal to n, I get a shape of, so it's now I had my half circles here, and I added this half circle which depended on a1 to an, but that's basically a1 to an determines a shape like this. And the question is, what is the probability? So you can start and go around either, I mean, at some point you will come back to the same place, but it could cover the whole thing, or this could be just a connected cycle. Of getting a connected cycle. Or two of them, or as n goes to infinity. Sorry, n it goes to infinity, and sigma I is equal to n. It's somehow a random point in the random point where AIs are integers. So, okay, so this is a little, yeah, so you can certainly generalize this kind of questions very easily into, you play with this a little bit, you see that you can very easily make this into a question about, there's nothing about this semicircle or the way you define it. You can start from a graph, and maybe I can, you can see even the interval in this. You can start from a graph, and you can have n incoming edges and n outgoing edges. And then you have this here, you can have a permutation to join the incoming and outgoing edges. And each, say, you want to make the problem easier, each incoming edge will go to, maybe I have 1, 2, 3, 4. Maybe 1 goes to 4, 2 goes to 3. And of course I can draw it on the plane, but it's okay. I look at the graph, 3 goes to 2, and 1 goes to 4. So, okay, it's just a graph. And then if you assign A1, A2, A3, A4, where the sum of AI is equal to large capital N, you can basically do the same thing that we were doing here, meaning that I can just put something very similar to that without using circles. I can just use this integer points AI to draw a parallel line. So if I have 1, and therefore I'm looking at the number A1, I'm putting A1 line parallel to the first one, and then I'm putting A2 line, not in the parallel, but A3, A4 here, and here I'm putting again A1, A2, whatever these numbers are. And I'm just connecting, and here I'm just using, I have now, because the sum is capital N, I have capital N stands here and capital N stands here, which are joined two different ways. So one way is just this here, without any subintersections, and the other way is through the line of the graph. So A1 to AN will determine a loop. And the question is, when is this loop connected? Or, what is the probability of, be more precise, probability of getting a connected loop as basically n goes to infinity. So maybe this will be true from A1 to AN integers uniformly by restricting that the sum is less or equal to n. But the probability of getting it, it's not that hard to get something connected. I just want to see what it means. You can put some conditions on these integers to see when it's connected and it's not. And to get a sense of this, you can do it in the simplest possible graph. The two, this goes here and this goes here. And if you have to put A1, A2, and A1, A2 here, and A1, A2 here, sorry. What I'm getting, so what I'm getting here is that so the loop is connected if and only if A1 and A2 are co-prime. So you get asymptotic that then goes to infinity. You get something about the probability of getting a connected arc, which is non-zero, which is the probability 6 over pi squared. You can calculate this with elementary number theory. But as you have more and more intervals and your graph is more probably complicated, then you can't use anything. You can't say you can't easily write in terms of AI. And yeah, but as you can see, this is of course secretly. There's a surface behind the surface, and the surface is the surface that you get by thickening the graph, which is a ribbon graph, and gluing basically this to get a compact surface. So for example, if I do this 1, 2, 3, 4, 1, 2, 3, 4, and this kind of thing is it's related to the interval space math, is something that people study a lot and have nice properties. But if you do it, for example, if you thicken the graph, this 1, 2, 3, 4 that I have there, and basically glue back a disk to make it a compact surface, you get a surface of 0, 2. So for the presentation that I have, or as I'm sure you have seen, if you do this kind of graph and you thicken it, you get a surface of -1. So these are questions related to some topological properties. things on surfaces. And so here's the third question is basically what a generalization of this, that you can start from a surface of genus V, and so you're looking at different maybe patterns on S3. And a pattern, I mean, it could be maybe the surface up to now with this S3 surface genus V, and I'm only interested in topology. There's no geometry on it. And it could be a union of homotopy classes of closed curves. So for example, you can have this guy, this guy, this guy, and this guy, this guy, and maybe some intersection in the middle in between. So this would be your gamma, and then you want to see basically, so whenever you can draw one picture like this, and even if this gamma either off homotopy, you have a very natural action of a very important group on the set of patterns of this type on the surface, and the action is by this is the mapping class group of which is the group of say diffeomorphisms or homeomorphisms here, orientation preserving or homeo up to isotopy on the set of patterns of this type. So all I'm saying is that if you have a very complicated homeomorphism, and I give you this picture, you can look at the image of this picture on the diffeomorphism. It preserves the height, the shape of this, and just makes it look, the length would be longer, but in fact they're not more complicated. It's whatever like self-intersection or whatever properties this has, the new pattern will have the same properties. For example, if you have one simple curve, it will be always simple, like 10 of them intersect in whatever way, it's basically the same thing topologically. You get the same thing if you cut the surface along the edges of this pattern. So, okay, so you have all the patterns of this type, which I write as mod G dot gamma topologically. And now I wanted, so if you want to try to understand, say, hyperbolic surface, I think hyperbolic surfaces are just hyperbolic, easier hyperbolic surface or hyperbolic structure here. Or maybe you have a negatively curved distance function or metric, or just something which is not positive, the curvature. You can basically look at the statistics of, so you can order your gammas. So these are, so another mapping class, so it's just you can think about it as a diffeomorphism up to isotopy. And you can look at the set of, order the set of G gammas, and then measure this, somehow the complexity of G gamma just by, if I give you a union of closed curves on a surface, you can do it by one way, if you have something which has negative curvature, by basically the length. So because if you have something which has negative curvature, every closed curve has a representative which has the minimum possible length, and that's the length of that curve. So that's a unique geodesic representing that, and then you write this as whatever, this is gamma tilde, L gamma tilde of X, where gamma tilde is a pattern of type gamma. And the type of questions are, first of all, maybe the growth of the length, or depending how it depends on X, or even more complicated somehow is how if you have, for example, two curves, alpha 1, alpha 2, in gamma is the statistics of the ratios of length. As the length of subset, as the length of the big guy, which is the union of all of them, tends to infinity. So, and because I won't have time to discuss these problems in detail and how you do them, I will just say here, for example, no matter what the complicated shape that you have gamma tilde is, you always get something, and I want to compare this with another result that I will mention. So the number of gamma tilde is of type gamma of length less than or equal to L grows like L to the, okay, so you have the genus L to the 60 minus 6. So it can be anything you want. But of course there are many closed curves on the surface there. I mean, for those of you who know that if the length grows, there are exponentially many closed curves on the surface of length is equal to L, but the point is that they become more and more complicated in terms of the pattern. And in fact, if the length is L, you likely have square root L step to section, so there's no way to get things about all, this is not about all curves. The same way as I should mention, this is not about all these kind of meanders that if you have seen in this, this is about the ones with of bounded type in some sense. And the same way these are about getting estimates about the guide of bounded type. So the type, the topology is not getting more complicated as the length grows, so it's a little bit different from looking at all possible curves. Okay. So and then finally, so these are things about surfaces that if you have like, so the first two are basically combinatorial and the topological, and the third one is like fixing. You have a fixed hyperbolic structure and you want to see some patterns in terms of the length statistics of the ratios and see if you can distinguish this different hyperbolic structures based on that or not. Okay, so finally, so these are the problems motivating this. So the finally get the billiards of type gamma. And the type of questions are, first of all, maybe the growth of the length, or depending how it depends on x, or even more complicated somehow is how if you have, for example, two curves, alpha 1, alpha 2, in gamma is the statistics of the ratios of length as the length of subsets, as the length of the big guys, which is the union of all of them, tends to infinity. So, and because I won't have time to discuss these problems in detail and how you do them, I will just say here, for example, no matter what the complicated shape that you have gamma tilde is, you always get something, and I want to compare this with another result that I will mention. So the number of gamma tilde is of type gamma of length less than or equal to L, grows like L to the, okay, so you have the genus L to the 60 minus 6. So it can be anything you want. But of course there are many closed curves on the surface there. I mean, for those of you who know that if the length grows, there are exponentially many closed curves on the surface of length is equal to L, but the point is that they become more and more complicated in terms of the pattern. And in fact, if the length is L, you will likely have square root L step to section, so there's no way to get things about all, this is not about all curves. The same way as I should mention, this is not about all these kind of meanders that you have seen in this. This is about the ones with of bounded type in some sense. And the same way these are about getting estimates about the guide of bounded type. So the type, the topology is not getting more complicated as the length grows, so it's a little bit different from looking at all possible curves. Okay. So and then finally, so these are things about surfaces that if you have like, so the first two are basically combinatorial and the topological, and the third one is like fixing. You have a fixed hyperbolic structure and you want to see some patterns in terms of the length, statistics of the ratios, and see if you can distinguish different hyperbolic structures based on that or not. Okay, so finally, so these are the problems motivating this. So the finally get the billiards. So the type of, there's several questions which are related to the dynamics of the moduli space, and it's hard to say much about them without using the moduli space. And that, I mean, these are about the behavior of, so the general problem is trying to understand the behavior of the trajectory of a ball in a billiard table. But this is a very this is very difficult, and your table maybe, I mean, if you don't put any conditions on it, could be anything. And it's a very difficult problem. There are lots of results that I won't have time to discuss. But so you have a point, and you hit the ball at this point, and then it goes and it bounces off, and the point, and it's in a billiard table, meaning that these angles are the same whenever you intersect the boundary. And you want to see what happens to this point. And are the closed orbits, are the orbits Are there dense orbits? Are the dense orbits spending a fair amount of time in all facets of the billiard? So there are many problems like this, but maybe instead of the billiard thing, first of all, instead of having a smooth thing, you can also look at even at the polygon billiard. And then whenever the ball goes to one of the, so basically the conditions are the same, the only difference is that whenever the ball goes to one of the vertices, it disappears. So you don't continue. So there are many finite trajectories. There is no way to continue, but whenever it hits the boundary, the angle and when it reflects, the angle, they are the same. So another problem which is related to this is, maybe I want to mention two other problems and then discuss the relation to this dynamic, called illumination and security problems on billiards. Okay, so there's one question, which is, again, these are quite old questions, that if you have a room and the walls are made of glass and you have one light source somewhere, doesn't necessarily make the whole room bright, or so of course if it's a convex set, it does. So you have a billiard, the problem then it might not be convex. What can you say? And then you have a point, and you're allowing, so light means that, of course there are variations of this question, but light means that you're looking at all the rays coming out of one single point, and you allow them to move forever. So it goes, and then it goes, it intersects this, then it goes, intersects this, of course, then it goes, maybe at some point comes to this corner, maybe not. But then you have all the possible, even P, so even P, you look at all rays starting from P, and you are interested in the possible setup, are the points not covered by this one source light, or what can you say about the set of points which are not covered? And in general, I mean, there are examples of actually billiards which are not illuminated at one point, but it's very hard to say what is set that can't be covered. For example, in many cases in the billiard, and I'll discuss this a little bit more, when the billiard is slightly nice from our point of view, then the set of points which are not covered end up being finite or at most countable. And okay, so that maybe before I mention these kind of results, I will say, so this is one problem. Another problem is that maybe you have a source and another point Q, and maybe there are many ways there could be infinite, I mean, there are infinitely many ways of getting from P to Q, maybe, but you want to see not only if it can get from P to Q, but can you block it? Can you block P, Q? So by this I mean all geodesics from P to Q in the billiard, and whenever you go to one of the vertices, it disappears by finitely many points. So if that can happen, for all P and Q, say the polygon is secure. So, for example, because maybe you don't want the thing from P to reach Q, for example, the security guard, and the president and the terrorist, and that, I mean, there's all sorts of interpretation. But you want to have finitely many blocks, so that any geodesic ray from P to Q, by this procedure, will go through one of these finitely many points. So you can imagine these are hard problems. And maybe this looks very quite unlikely, but the torus or square is secure. And of course, you can do this even on manifolds. Like if the manifold, you have 2 points, you want to block all the geodesics going from one point to another by finitely many points. Is it possible that for any 2 points, there are finitely many points that any geodesic between these 2 points will go to one of these finitely many points? So conjecture is that there's a lot of actually work on this area. Maybe I'll refer to Hawkins as a reference. And the conjecture is that for a manifold, that means a Riemannian manifold, and I'm not sure if, I mean, I'm not convinced it's true, it's secure if and only if it's flat. And I think it's known that if it's flat, then it's secure, and there are lots of examples where this happens, that it's secure and flat. But in our setting, I mean, this is a simple little exercise to do that. Any 2 points, there are lots of, all the geodesics in this billiard, from any given 2 points, then there are finitely many points, and you can imagine these are basically the middle of this guy, and then you can draw some other finitely many geodesics, and the middle guy will be the middle of all the geodesics between these 2 points. Simple exercise that you can do. But by geodesic, I mean rays. The here, so it's a more general thing about geodesic if you have the Riemannian metric. But here, geodesic means that with respect to the flat surface are. So there are lines. Of course, this is one, but there are more complicated ones because something can go hit the boundary several times, right? And then end up at the other point. These 2 points are fixed. These 2 points are fixed. And the question is,
We'll be back in a bit.
so that
Set up
anyway,
kitchen
you go from this point to this point, you go to one of the finite remaining points. And this is, yeah, this one is very